Hello, I just wanted to do another video quickly, not on a particular topic, but actually on this question that many students ask, how do I study physics? Like most students think that physics is just another math class. No, it is not. I wish it was. It's a lot more different than math. We use a lot of math, but here we have a lot of critical thinking. I'm just going to take the example of speed of sound in order to do this. So let's get there. So we will look at what is the speed of a wave. If you simply look at a formula, the speed of a wave could be given as the product of frequency and wavelength. So you would write it as velocity or speed is equal to f times lambda. So that is a Greek symbol for wavelength. So then when you study, you should know what each symbol stands for. So you would go, V is for velocity, which is also speed. F is for frequency, and then lambda is wavelength. But you should also go one step further. You should look at the units of each quantity. Units are very important in physics. So you would look at, velocity, it should be in meter per second. Frequency, it's hertz. And what's hertz? That's the name of a scientist, but what is that? And wavelength is a length, so it should be in meter. Wavelength. Now what's hertz? Hertz is the number of waves in 1 second. So you have to go deeper even when you look at the units. You can't just go, it's hertz. You have to know hertz is the number of waves in a second. Okay, so what next? So you just know this formula, you give one frequency and you give one wavelength. Can you find the speed or velocity of the wave? Yes, we can. But let's look at a wave before that. That is a wave, so that's one wave. Here is another wave, so you have two wavelengths shown. So those are two wavelengths. So that is one wave. This is the second wave. So there are two wavelengths shown. So I'm trying to say that from A to C is one wavelength, and from C to E is another wavelength. So there are two wavelengths shown, right? Okay? And imagine that the wave is moving from left to right. So if the wavelength is 2 meters and the frequency is let's take it as 5 hertz, what is the speed of the wave? Okay, now it's simple math. It's 2 times 5, 10 meter per second. How do you get meter per second? Because hertz is number per second. So when you multiply the units, it becomes meter per second. See, that makes so much more sense. All right, that's point one. Now, up until this time, the student in studying has done a real good job. But is this enough? So now I ask you the next question. Hey, what if the frequency becomes 10 hertz? And we are talking about the same material. So the waves are traveling through the same material. Maybe sound traveling through air. So it's the same material. And the frequency becomes 10 hertz. What will the speed be? Without thinking, students could go, okay, so now it's 2 times 10, 20 meter per second. Is that the answer? Let's find out. See, if you simply treat it as math, that's where you will go. You will go, okay, 2 meter times 10 is 20 meter per second. But if you do a little bit of thinking, you will see that, no, the answer is not going to be 20 meter per second. Let me show you why. Velocity of sound, because we're using sound, and sound is a wave, velocity of sound depends on the material. Now, since I said that the material did not change, the speed of the waves must remain the same. I'm going to prove it. the speed must remain the same because the speed depends on the material. Oh, it did not change the material. How does that work? That works because when the frequency becomes 10 hertz instead of 5, so the frequency doubled, the wavelength becomes half. Because you have more number of waves per second, the wavelength becomes smaller. I hope that makes sense. In air, so we're taking speed of sound in air as the example, it's 340 meters per second, okay? And the frequency is 100 hertz. Can you find the wavelength? Speed of sound in air is a constant at a particular temperature, we'll come to that soon, and it's 340 meters per second, and I give you the frequency as 100 hertz. Can you find the wavelength? Of course. Wavelength is velocity divided by frequency, so 340 meters per second divided by 100 will give you 0.34 meter. Good. So what if the frequency now becomes 200 hertz? Remember that the speed remains constant. So if the frequency is 200 hertz, then the wavelength is going to be 340 by 200, which is 0.17 meter. Now here's a picture illustrating what we've just calculated. So you see that in the first case, when the frequency is 100 hertz, the wavelength is 0.34. And in the second case, when the frequency is double, the wavelength became half. All right, so now it's getting better. We do know that the speed depends on the frequency and the wavelength, but we also know that the speed of a wave depends on the material through which it is passing. I hope that is making sense. Well, up to this point, we have done a lot of good thinking, but is that all? No, let's take it further. So now the question is velocity of a wave through a material a perfect constant? So, like velocity of sound in air is 340 meters per second, but is it always 340 meters per second? If you were listening to me, you would have heard me say something about temperature. So now we have to say, no, it's not always a constant. It's only a constant if the temperature is constant. So what if the temperature changes? How does the speed of sound change? All right, let's find that out. So we are digging deeper now. So the velocity of sound in air depends on the temperature. So we have another formula for that. And now the formula is going to be velocity at T Celsius divided by velocity at 0 is square root of T plus 273 by 273. Okay, T is in Celsius. T is the temperature in Celsius. And V naught, which means velocity of sound at 0 degrees Celsius, is 331.3 meters per second. So using that information, I'm now calculating the velocity at 30 degrees Celsius. Okay, let's slow that down. Velocity at 30 divided by the velocity at 0, which is 331.3, is square root of, remember T has to be in Celsius, so that's 30 plus 273 by 273, which comes out to be 349 meters per second. So we see that as the temperature increases, the speed of sound in air also increases. So we do some thinking there. Oh, if it's cold, speed travels slower. If it's warmer, like in summer, sound travels faster, right? Is that all? No. We can think a little bit more. We will be like, are there other factors on which the speed of sound depends? Is it only temperature? The answer to that is no. There are other factors. So let's look at that. So what are the other factors? The speed of sound in air depends on the pressure. You know that the atmospheric pressure can change from day to day, from time to time. So assuming that the temperature is constant, we're going to look at how the speed of sound depends on the pressure. In fact, when you study the dependence on pressure, you also have to consider the density. You know how compact it is? Like at the ground, air is more dense. If you go higher, it becomes less dense. So it depends on pressure and density given by this formula. Speed is square root of gamma p by rho. Wow, what is gamma? Gamma is called the ratio of specific heats. That is from semester 1. Yes, the ratio of specific heats. And for air, gamma is 1.4. See, I could have talked a lot more about specific heats. I'm not going there. It is the ratio of specific heat at constant pressure divided by specific heat at constant volume. So do you see that every topic in physics is actually related? Okay, anyways, for the time being, gamma is 1.4 for air because it's diatomic, and P is the pressure. And you know, this thing looks like P, it's not P, it's rho. It's Greek, rho, for density. So please don't cancel it out. P is pressure, rho is density. And so at 1 atm, which is actually 101,325 pascals, that's what 1 atm is, let's find the speed of sound in air. Okay, so we have to know that the density, or will be given, the density of air is 1.29. And so we have gamma, we have the pressure, divided by the density, and that comes out to be 331.6 meter per second. Wow. So now we've looked at the first formula for speed, which was frequency times wavelength. We talked about that. We looked at how velocity of sound depends on the temperature. And then assuming that the temperatures are constant, we looked at how it depends on pressure and density. So here is a question that could be asked. You know, and this would be the ultimate in critical thinking. So listen to the question carefully. I think I've written it down. If you have air in a cylinder fitted with a piston, and if you slowly compress the air, compress it to half of its initial volume, that means you're increasing the pressure, aren't you? So when the volume becomes half, the pressure becomes double. Yep, Boyle's law. So here the question is, first I said a gas cylinder, I changed it to, it's not air, it's air in a cylinder slowly compressed to half the initial volume. How does the speed of sound change? So people can think, students can think, you know, oh yeah, the volume is half, so the pressure becomes double. And so then they will go, oh, if the pressure becomes double, then the speed of sound should become square root 2 times, right? Because it's under square root. But you know what? The answer is the speed of sound does not change. It will not change in this case. You want to know why? Now you're thinking about, hey, but didn't the pressure double? And if the pressure doubles, shouldn't the speed of sound change? No. Why? Because the density, which is in the denominator, also doubled. When you compress air, yes, the pressure doubled, but the density also doubled because you have the same mass of air in half the volume. So the density became double. See how you have to think? So I'm just trying to show you that it's not math. Not just math. Math is important. So if the numerator and the denominator doubles, they cancel out, and that means the velocity is a constant. Okay, let me prove that. So pressure times volume is nRT, the ideal gas equation. That's what I'm using. And I'm dividing both sides by the mass of air in the cylinder, could be anything. And on the left side, because you have volume by mass, see that? Volume by mass is 1 by density, okay? Volume by mass. So that's P by rho. And on the right side, all of these quantities are constants. The number of moles, the universal gas constant, temperature in Kelvin, and the mass of the gas. All are constants, so I'm not interested in those numbers. All I want to know is, oh, P by rho is a constant. If P by rho is a constant, and the speed of sound is square root gamma P by rho, gamma is already a constant for air, and P by rho is also a constant now, that means the speed is a constant. That's all I need. That's all I need. So is this the ultimate? Well, if you're taking college physics, please stop at this point, but I want to take it a little further. And if you can think, you can go along with me. I mean, think even more. It's deep. All right. So with all this information, finally, let's calculate the speed of sound in oxygen at STP. So now it's not air, it's oxygen, and it's at STP. STP means standard temperature and pressure. So the standard temperature is 273 Kelvin, and standard pressure is 1 atm, okay? So shall we try to find the velocity of sound through oxygen at STP? All right, we know P by rho is nRT by m, and we're considering 1 mole of the gas, so N is 1, 8.314 is the gas constant, and then T is 273 because STP means standard temperature, okay, which is 273. So I get that number, and then once I have P by rho, I can find velocity as square root of gamma P by rho. Gamma is 1.4 for oxygen because it's also diatomic, and that gives 315.1 meter per second. Wow. So the speed of sound in oxygen is less than in air at 273 Kelvin. So remember that in this part, I was not trying to teach you about the speed of sound, though I did. I was just trying to show you how to study for the exam.